All right. Hello, ladies and gentlemen, and welcome. Uh, Actually, recording this Sunday night. Had to try some different recording software, so we're going to see how this goes. Anyways, so here we are, Physics 11, and we're going on to waves, taking a look at waves. And we'll be finishing off the waves. We may get into sound. We'll see how it goes. Um, it's a pretty important I think it's a pretty important topic. When I was doing my physics, we had a whole course that was dealing with waves. And you might think, well, waves, where do we find waves? Like we find waves on water. And, do we find waves elsewhere? Well, okay, yeah, sound. How about elsewhere? Well, light is, okay, that must really deal with it, right? Except if you then consider vibrations, any vibration deals with a wave. So, earthquakes and vibrations in your car engine. All these different things are dealing with vibrations. Vibrations can mean loss of energy, uh, and if you're losing energy, that can cause problems. You want to sometimes keep things as efficient as possible. So waves are really, really important to see. Like when we get into waves, we have radio waves and radio waves, transmitting sound and pictures and so on over through electromagnetic spectra and stuff like that. So big, 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 big topic, and you get a taste of it. That's really what's going on. But really, before we can talk about waves, we want to talk about two topics, frequency and period, and just to talk about how they are related. So frequency. Uh, the well, what we call the cycles per second. How many times does something happen in a period of time or in a given amount of time? So I read 3 books in 1 month. There's an end. That would be a frequency. It's something that happens, what we call a cycle. Generally, it's like a repeated type of motion or a repeated something. And then we have time on the bottom. Uh, if we were to take a look at a pendulum is swinging back and forth. There is things that are happening here repeatedly. And so we can talk about the frequency of this in terms of it swinging back and forth. The general unit of frequency and the symbol that we use for frequency is a lowercase f. And the unit is called the hertz, symbol Hz, and it's defined as being cycles per second. And so, where you might see this, well, if you're buying a computer, and you might read about, well, it's running at 2.3 megahertz or gigahertz or something like that. And within the computer, what's happening, what this refers to, I like to think of it, if you've ever watched, well, a band play or something like that, you have at the front of the band, you have the conductor, and he's got his baton. And his baton waves back and forth. The faster he moves his baton, the faster they play the music. The slower he waves his baton, the slower the music plays. That's one way of thinking about it. So inside a computer, there is like a conductor, a clock, that controls how quickly the computer does its work. And the larger this number, the faster this number, potentially the faster the computer. The radio, if if you're listening to, I don't know, like 97.3 or something, or 93.7, CBC is 93.7 megahertz. And this is what we call the frequency of the carrier wave that's carrying the sound and music and everything like that to your radio. And so these waves come into the radio, and you've got your radio takes those waves and then makes the music come out and the sound come out of there. And it's doing this with the radio signals. So these numbers actually have physical meaning, measured meaning, and we talk about those as the frequency. So the period is the time for one event or for one cycle. So, if we're to take a look at our period, we can turn on what's called a period trace. And so the period trace shows us, you can see when it traces out, goes across and comes back. That is the full cycle. Now, this always shows the period is starting from the end, but you can think of it starting from one end out here. It goes out, back, and back out. And that would be what one period is for a pendulum like this, or a kid on a swing. So the time for one cycle. And so we have, the kid who's on the swing, whee, and he goes out and he comes back, and that's what we would call the period. And the period is okay. So the period, the symbol for that is a capital T, and that's measured in seconds. Well, I know what I should do. So let's do this. So a child completes 20 cycles in 25 seconds. And he's on a swing. So this child's on a swing, going backwards and forwards, and he goes 20 times in 25 seconds. What we want to know is, what is the frequency? And to do that, well, the frequency is cycles per second. We're going to take our 20 cycles divided by our 25 seconds. And pointing out Casio FX260 solar, we can see that that's going to have a frequency of 0.80. And what's the unit? Well, cycles per second, hertz. Well, we also want to know what the period is. And the period is the time for 1 second. So we're going to take our time, 25 seconds, and we're going to divide that by our 20 cycles, the number of events that happen. And so if we take our 25 and divide that by 20, we get 1.25. 1.25 what? Well, seconds, and you can think of this as being seconds per cycle, but we just only talk about period in terms of the time. It's the assumed time for 1 second. So what that means is that the child is here, go here, swings out, and then swings all the way back, and that takes 1.25 seconds. To do that last minute, there we go. Takes 1.25 seconds. The period, how many times they swing in a unit time? So it takes 0.8 seconds, or in 1 second, this child will go 0.8 of the full period, or the full motion that he's doing. The full motion takes 1.25 seconds. Now, you might have noticed that here we have 20 cycles per second, and here we have 25 seconds per 20 cycles. The same numbers, and we're just applying and we're taking a look at them differently. And so what that talks about is that we have a relationship between period and frequency. And we can say, well, the period is 1 over the frequency, or we can say frequency is 1 over the period. It's an inverse relationship. Can't spell relationship tonight, but that's okay. All right, so we said that the period was 0. No, let's do the other way around. Where's my eraser? There we go. Back to my pen. All right, so if we wanted to know what the period is, given that the frequency was I'm trying to remember my numbers, 0.8 hertz cycles per second. So we can go 1 divided by 0.8, and that gets us our 1.25 seconds. Likewise, if we want the frequency and we have the period, we go 1 over, well, the period was 1.25, and we go 1.25 divided by 1, and we're going to get 0.80 hertz. So this is the relationship. So period and frequency, an equation we need to know. For repeated motion, and this is where we're using it, the period, the time for one motion, 1 over the frequency, or the frequency is 1 over the period. A tuning fork. Oh, that's not what I wanted to do. Let's do this. A tuning fork. Now, a tuning fork is a piece of metal, and it is in the shape of a U, basically. And what happens is that you give it a strike, you bang it on the side, and the forks, the tines, vibrate back and forth. And because they're the same length and the same mass, they vibrate with a particular frequency, and you have a frequency and there'll be a characteristic period. Now, tuning forks are used for tuning musical instruments. So you have, if you play the piano, you know you have different keys, A, B, or different notes, A, B, C, D, E, F, G, yeah, 8 notes. And you have an octave, and that octave gets repeated, and it goes progressively higher, but always 8 notes, 8 notes, and 8 notes. So you'll have, so we talk about A, and A vibrates at 440 hertz. This, you're going to have, so this is an A here, you're going to have another A, and it's going to be vibrating, if I remember correctly, yeah, at 880 hertz. Twice what this is. And then up here, we're going to have, well, it's going to be a little higher than that. And so what we get is that we get this doubling of the frequency of these notes as they go up through the octave. But we have this tuning fork. So what we're told is that a tuning fork vibrates 24,000 times in 1 minute. And what we want to know is, what is the frequency and what is the period? All right, so if we want to do frequency I often find is easier to think about, easier to follow. Period is an important thing for us to be able to calculate. Conceptually, it's sometimes harder to grasp. Let's deal with frequency. Frequency is the number of times something happens in a period of time. So we have this 24,000 times, 24,000 cycles. Frequency, though, we want to be in cycles, in hertz, which are cycles per second. So what's 1 minute in terms of seconds? Well, it's going to be 60 seconds. So if we go our 24,000 divided by our 60, 24,000, I just had my calculator lie to me, divided by 60, and what we find is this is equal to 400 hertz. That's the frequency. Well, what's the period? Well, you can take the period and say that's 1 over the frequency, so 1 over 400, and we get a value of 2.5 times 10 to the negative 3 seconds. This is vibrating 24,000 times in 1 minute, 400 times in 1 second. Yeah, the length of time for one vibration is going to be very, very small. All right, let's continue on. Waves on a line. So when we're dealing with waves, and we're going to come back to the repeated motion of a pendulum, where are we going? Pulse wave. So we're dealing with waves on a line. So that line might be like a spring, or a string, a cable. If any of you have been out, or like if you ever play guitar, when you play a guitar or a musical instrument, you have the strings, you have the wires, and you tighten them up. And so you've got a tuning thing that tightens them up. And when you pluck the string, the tune gets higher and higher and higher. And that's because we're creating a wave on this string and it's vibrating. And it has to do with the tension and so on. So there's the amount of force that's pulling the string changes what we'd say the tone is, or changes the vibrations that are happening on a string. But there's different ways of generating that spring. So we can talk about, first of all, a pulse wave. And a pulse wave would sort of look something like this. So we have our spring, and what we've done is that we've moved the spring up and then back down again, and so we get this wave. And what happens is that this wave travels. And so if we took a look at just a second later, we would find that the wave, that pulse, is in a new location here. And take another look, another second, it's on a location there. And then it keeps on moving. And so what we have is that the spring itself, the wire, is moving upwards and the wave is moving sideways. Now, we can go to here. So here we have this fancy piece. So we have this series of beads along this line represents our spring. And it's held in a clamp right now. And we've got a wrench. I'm not sure why they're using a wrench. But now if we create a disturbance, and I create a disturbance by moving up and coming back down again, we can see that that pulse moves along the spring, along these beads. And you can also see it dies out. Now, this is where this damping comes in. The damping is how quickly it dies out. So if we change this damping to a lot, look at that, it doesn't even make it there and back. And if we change the damping to none, then you can see the wave just keeps on going and doesn't, like here we have a reference line up here, and it never gets any less because the damping is 0. Now, in reality, we never have damping that's equal to 0, so let's give it a bit of damping. And so we can see that it gets smaller and smaller and smaller. But we can create the pulse, and it travels there. Now, some of the things that we can recognize here, this clamp represents a fixed end. This is tied, it's being held there. And so when we create the pulse, you'll see that the pulse goes up, hits here, and then the disturbance, let me turn this down a little bit. I want 0, there we go. I want 0. Oh, this is nasty. Can't get in between. Okay, best will do. So it gets less and less, but you can see in essence the wave seems to flip over when it reaches the end. Now, if we change this, so up here we've got the opportunity. There should be a link to this in the email. So you can come in here and you can play with it. And that's, if we were doing this at school, I've got the springs, you've seen them before. We've done a little bit of waves, perhaps if you remember back in Science 10. No, at some point we did some waves, Science 8. And so you might remember some of these things from them. But we would be doing this with an actual spring in the classroom. We'd be taking a look at this. So now we've got a loose end. And so now if I create the wave, you can see that on the fixed end, this is now the fixed end, it flips over, but on the loose end, it stays upright. It's only on the fixed end that it flips over. So if we have a fixed end, the disturbance flips over when it reflects backwards, and it's a loose end, it remains upright. There we go. Cool. Excellent. So we have this pulse wave. And so, yeah, we've got a pulse wave, which is just the pulse that's going. And so But let's talk about what we call a transverse wave. So now we're going to come and we're going to call this an oscillation. And so you can see that we've got a rhythmic, a repeated pattern moving up and down. And I'm just going to pause this for right now. And so this is what we would commonly see in terms of looking like, wait, I couldn't have stopped this better if I tried. So it comes up and then comes back down again, and then comes back up and comes back down. And so this is a characteristic of what we call a sinusoidal wave. Now, some of the things down here, we've got frequency. Hey, we've been talking about frequency and period. So we're talking about how quickly this moves up and down. How many times does this move up and down in a period of time? All right, so here we have our wave. So we need to come back and just make sure we've got some terminology to this. So here we have our wave, and so let's draw a wave. Not very good at, but close enough. Okay, so we have this line through the middle, and this line through the middle is what we call the rest position. Now, if you can remember some of these things, that would be great. The rest position is where, if there was no disturbance on the string, that's where the string, that would be this, like the surface of the water, we're looking for the side. This would be where the spring hangs without anyone creating the wave on there. And so then we talk about the distance from the rest position to the highest point, and we call that A, our amplitude. Or here's A, our amplitude. So A is the amplitude of the wave. Now, if you want a characteristic or something you can think of as the wave, think of loudness. How loud is the sound? A loud sound would have a high amplitude. A quiet sound would have a low amplitude. And so we can talk about amplitude as the loudness and essence of the wave. Now, we can also talk about the period of the wave. And the period of the wave is from one point on the wave to the next point on the wave. And that's what we call the wavelength. And the symbol that we use for that is a Greek letter, lambda. Lambda. And that's for the wavelength. Wavelength. Let's try it again. So, you know, things are starting back up at school, and you'll have opportunity to be coming in sort of once a week. I'm not sure how that's all going to be organized starting June 1st. But hey, you're more than welcome to pop in. And if you're having some difficulty, wants me to go over some things with you, you know, that we can sit down and do that. It's not going to be regular teaching. It's not going to be a lesson, or I'm still going to be doing things distance and doing videos and so on like this. So just be aware of that. All right, so we talked about the wavelength. Now, if I take this wavelength, oh good, it works. So we can say that's from a repeated place. And so we can take a look, and it really should be from here over to here. So my wavelength was changing, but that would be a wavelength. And likewise from here to here, so we can see that here it's coming up, here it's coming up. So that represents a wavelength. Here it's coming down, and I really drew this badly. So this should be where it's coming back down and so on as well. I was not very consistent in my drawing. Anyways, so that's the wavelength from one position on the wave to the next position on the wave. If we come back to here, let's get this going again. So let's take our frequency. Let's take a look at what happens to our wave if we increase the frequency. So I'm going to pull this up. Okay, what's changed? Has the amplitude changed? Not really. So if we're back down here, give it time to adjust. this is actually kind of interesting. If you're taking a look at how the driving arm here, it only goes up to this line. The amplitude actually goes above the line and drops down below. That's okay. So if we make this slower, where's the wavelength? Let's pull it up. So here we have. So what's the wavelength like here? Oh, the wavelength is pretty long. It's on the order of at least here to here. It might be longer than that. If we increase the frequency, you can see the wavelength has decreased. And so it's, here it's quite apparent. You might not have seen this. So here we have the wave going, and we can bring it back down. Takes a while for it to adjust, has to dampen out the old perturbation, the old movements. So now we've got the wave, and we can see that here we have like the amplitude. There's still the amplitude there, but yeah, it's not moving the same way. So frequency comes into this. So so frequency, where's my pen? Here we go. Frequency, or let's say high frequency, short wavelength. Low frequency, long wavelength. And if you remember electromagnetic radiation, we talked about this as well. Here we go. That's all right. We'll just scribble over it. This was something that we talked about in electromagnetic radiation, and we were talking about the like Roy G. Biv, and this was long wavelength, low frequency, short wavelength, high frequency. And we remember we talked from like radio waves all the way up to gamma waves, long wavelength, low frequency, short wavelength, high frequency. I'm sure you guys all remember that. All right, let's compression waves. Compression waves, an example of compression waves are sound waves. And I think I got a video on that. Let's pause this right now. Here we go. So this is a compression wave. I've sort of tuned it up. So here we have the spring coming across here, the slinky. You're going to see on compress. He's going to make a compression, and it's going to release it. And they're doing it in slow motion, but you'll see it travel. It's sort of a blurry spot, travel down the wave. Now this is not moving sideways. This is moving along the length of the spring. Let's see if this works.
That is not the medium that moves, only the vibration. Here, the compression in the spring moves from one end of the spring to the other, but the spring itself does not go anywhere. It's the same for sound waves that are generated in air. The vibrations travel via vibration of air particles, but the...
Okay, so we saw, I was just tracing along it with the cursor so you could see sort of where that compression was traveling. And so if we talk about, so we'll often use like a spring like that as an example of a sound wave. And so we'll use vertical lines and we'll spread them out and then use vertical lines. So this repeated sort of motion, and look like this. And so we talk about where the lines are close together, that's a compression. And so if this was in air, it would be the particles of air that are getting pushed together. And then the area where the particles are being pulled apart, or where the spring is pulled apart, it's called a rarefaction. So, and if we wanted to talk about the wavelength, we would talk about from compression to compression as being the wavelength for this. That's how we would deal with this. So if we come back to here, what we have, this is a transverse. We never mentioned that. Transverse means at 90 degrees. And so what it means is that our amplitude and our velocity is along this direction. we saw for the repeated wave, as the wrench was going up and down, the waves were being propagated and they were moving away from the source. That was our velocity. And so, if we were to take a look at the next moment, it would be moving like this dotted line. Following the pattern, but we know that I've not drawn this section through here. And so we have the idea the wave is moving in this direction. So we have the velocity of the wave, but when we talk about the amplitude, the disturbance is at 90 degrees. So that's why this is a transverse wave. In a longitudinal or compression wave, or the other term for it is longitudinal. What we have is we have our amplitude in essence in this direction, and we have our velocity also in the same direction. So they're going along in the same way, in the same direction. So that's our compression wave. Books never talk about torsional waves. They always talk about transverse waves, or they'll talk about compression waves. They never talk about torsional waves. But hey, torsional waves. Torsion means twisting. And here again, we can have twisting that happens within springs, within mediums, and so on. Oh, medium. What the wave travels in. So, water, you see a water wave, water is the medium. Sound, for sound waves, we have air. You could have a spring or a string. That would be the medium for the wave. Now, what's moving on that spring? This is something I haven't talked about either. But what's moving, so here, the movement of the spring is left and right, or up and down, where we have talked about the velocity of the wave moving this way. What's moving is energy. So this spring, if it was attached to something, can cause it to move up and down. It could do work. So we've got energy that's being transmitted by this, but the spring itself, or the string itself, the air molecules are not, they're moving back and forth, but they're not, it's not like the air molecules from here fly through the air and hit your eardrums. It's not the way it works. It's the vibrations, it's the energy that gets transmitted by the sound waves or by the spring waves that cause it to go. But anyways, torsional wave. Happen to have this demo set up here as well. All right, so what we have these two people. They look far too happy, and they're not even in the science room. They're in a band. Oh, it's elementary. Nothing real happens there. So what they have is in the middle of this, they've got a piece of material, and then they have all of these sticks going across. And the sticks are there just to show their torsion. So we're going to watch this and see what happens. She's going to take it and she's going to hit this one end.
That's so cool.
So cool.
Can you just say how you made it?
With great difficulty.
How long did it
Only
take?
one lolly got eaten in the process. It was stunning.
That's a miracle.
Well, so the kids made it, obviously, because it's perfect. I helped it. So just a strip of sellotape.
Yeah.
And then we've kind of went every 2 centimetres and tried to make sure we got them evenly.
Yeah.
And I think the lollies are actually there in case it's not balanced. But
So these are foreigners, and they're using bad language, lollies and things like that. Yeah, I'm prejudiced against British people with their accents. All right, so there we go. We're done for today. We've got some of those things. So we have frequency, we have period, we have transverse waves. and we have a bunch of vocabulary for that. And then we have longitudinal or compressional waves. Longitudinal. Now, and yes, torsional. Now, when, so these are all waves. They're all going to have periods and amplitudes and different things like this. If you think of just torsional waves as your classic example of waves, you're going to be fine. You're going to be fine. It's a good mental image to be dealing with. So we're going to be talking about waves, and we're going to be talking about wave phenomena. And I like the word phenomena. Phenomena. Anyways, phenomena, things that waves do. They reflect, they refract, they diffract, and they interfere. And so we have 4 wave phenomena that we're going to be dealing with. And if you can show something does those 4 phenomena, then it's a wave. Now, light is really kind of interesting because light behaves as a wave, and light reflects, light refracts, light interferes, and light diffracts. Some of those refract and reflect, you know. Diffract and interfere, you haven't dealt with. Wave does all those things. So what does light travel through? What's the medium? And that's a big question. Actually, I'm not going to answer it. What is the medium for light? All right. Homework. Yes, homework. This is in some ways a lengthy chapter because it's important. So this is the review, 18.13. I believe you have that. And I'm going to assign questions 1 to 9. You'll have 2 days to be working on this, Monday and Tuesday, and then we'll come back Wednesday and see where things are at. Again, if you have questions, talk to me, and we'll get things figured out. For the quiz last week, I know there was, well, Isha found a couple problems, shot through was 3, 1 wasn't a problem, and then Levi was saying, sir, I keep on getting the wrong answer, and I had a rounding error in my answers. And so that was really throwing things off, made a silly assumption. Anyways, so if you haven't done that, get it done. That would be a good thing. All right, I'm talking far too much. This has now been 38 minutes. Gotta go. Stop me. Stop it, Mr. Johnson. Stop recording this. Okay, have a good day. Bye-bye.